What I'm going to talk today is basically understanding neural networks with this tool called algebraic geometry. So for I think a third of this talk is going to be devoted to basically understanding what is algebraic geometry and what we can do. And also I need to mention this last paper is a joint work with Giovanni and Kathlén, and they both are in Zoom. So yeah, without any further ado, let's see what we have. The first thing that I want to mention is basically what is algebraic geometry. It's hard to say what is algebraic geometry because it's quite a big field, but for the sake of this talk, which is about neural network, I'm going to simplify it as much as possible, only talk about the properties or the features that we really care in machine learning. So algebraic geometry is simply understanding the zeros of polynomials. And for instance, if you have like k polynomials in n variables, you want to understand what is the zeros of this, common zeros of these polynomials. And right away, you get geometry based on this. And also, you get an algebra. So the algebra side comes from the coefficients of these polynomials that you have. And what happens is that algebraic geometry tries to connect these two universes, basically. So whatever phenomena that you see by your eyes from the geometric perspective, we have the language in algebra to describe it. So yeah, that's the simplest definition of what is algebraic geometry, or at least the basic motivation in classical algebraic geometry. And right away, that's the question that why should we care about algebraic geometry? So I came up with three straightforward reasons. The first thing is that you all know this is Stone-Weierstrass theorem. It says that any continuous function on a compact domain can be approximated by polynomials. In machine learning, everything is about polynomials, so everything about approximation, so polynomials have these properties. And the second thing that I came up with is this some of the constraints that we might impose on the architecture, something like rank condition. So rank condition is an algebraic condition, and also a sparsity. Or if you want to just impose some symmetry, for instance, in this equivariant network, these are algebraic conditions. And the third reason is basically understanding the optimization process, this critical point. So we have this powerful tool in algebraic geometry, which is metric algebraic geometry, and Kathlén authored one book about this metric algebraic geometry. So we can understand and quantify the number of critical points in a specific setting, basically. And just one simple example, we are going to see a lot of examples. So one simple example is the space of rank R matrices. The space of rank R matrices can be seen by the zeros of some polynomials, and they are R plus 1 times R plus 1 minors of the matrix, basically. So you get a bunch of polynomials. If you see the common zeros, they describe this space of rank at most R matrices. Now let's move on to more interesting examples. So we are limited to 1 or 2 dimensional. I cannot show higher dimension, of course, but I try to give you some of these features, tell you some of these features that are important in our setting. So the first example is like a line. So it's again an algebraic variety. So it's a common zero of y minus x equal to 0, basically. So or y equal x. So it's like a degree 1 polynomial that give you this line. And you can construct ellipse with degree 2 polynomial. And you can go further, degree 4, degree 7, your variety becomes more sophisticated. And also you can, of course, construct surfaces, for instance. And the features that are interesting for us, I can list a few of the features that we can study with algebraic geometry. The first thing is dimension. So these curves have dimension 1, the surface has dimension 2. we can also analyze or understand this dimension with the algebraic tools that we have. The second thing that might be new is called degree. So degree of a variety, or in some sense, a volume also. So as you see, when I increase the degree of these polynomials, the space becomes more complicated in the sense that it becomes more twisted. So we have a measurement in algebraic geometry to basically quantify what is a degree or kind of volume of that space. It measures how much your space is twisted. And the most important thing that I want to talk, especially today, is singular points. So we call the point in our variety singular, which basically is not regular, for instance. So I just try that to show it to you. For instance, in here, in this degree 4 curve that we have, this point is singular because if I look at the tangent space at this point, it is not normal. So we have like 2-dimensional tangent space. So we have singularities. While the other points, like another point that I take a smooth point of this, is 1-dimensional. And also for degree 7, you see that we have like different types of singularities. So this is called cuspidal singularities, which I explain a bit more in future slides. So we can analyze this type of singularities not only for curves, but also for surfaces, even in higher dimensional varieties. So in this setting, in this Whitney umbrella variety, which is the surface that you see, that point, that blue point, is also a singular point. But this type is quite interesting because in one direction, in one principal direction, we get infinite curvature. In another direction, it's just not infinite, basically. So we can have many different singularities. And for the purpose of this talk, there is a big difference between this cuspidal singularity and this nodal singularity. Okay, so we are going to focus on these 3 features today. And since our models are parametric, we are going to discuss about parametric models in machine learning, I also need to talk a bit about parametrization. Imagine that on the left, I'm trying to parameterize an elliptic curve, so see what happens. So I consider this polynomial equation, and I can parameterize it as following. So I have my parameterization from real numbers to R2. So I send every t basically to the following. And as you can see, this this parameterization give you this, the image of this parameterization give you this object, this curve. And we get this point that is not regular again, right? So we want to see what's the reason behind this. This parameterization is basically injective almost everywhere, except when I look at this phi inverse of the origin, it consists of 2 points, -1 and 1. The preimage of every other point is just unique. It gives you only 1 t, basically, except the origin. So what happened is that I have this line, I have this R in the domain of my parameterization. I identify 2 points, 1 and -1. So if you put t equal to 1 or -1, it gives you the same point. So that's how I get the singular point, right? So this is one way to get it. And if you look at this parameterization map phi, it doesn't have any critical point. So the rank of Jacobian doesn't drop if we compute the Jacobian. So we quickly realized that having an unusual fiber like this led to have singularities. So fiber of parameterization is important. So I call this fiber, understanding fiber. Having an unusual fiber in this setting gave us a singularity. And I switched to another curve, which is a cuspidal curve. So imagine now that you have the following polynomial equation. y squared equal to x cubed, you can parameterize this curve by the following. So I call this parameterization phi. So t stands to t squared and t cubed. This map, so psi is injective. Unlike the nodal cubic curve that I had, that wasn't injective at 1 and -1. It gave us the same point on the curve, but psi is injective now. But what happens in here that we still get a singular point. This singular point is not because psi not being injective or something. It's because the Jacobian. So the Jacobian of this parameterization, if we compute it, it gives us 2t and 3t squared. If you look at t equals 0, the rank of Jacobian drops. And because of that, we get this infinite curvature in here. So we get a singular point that caused by critical points of the parameterization, even though that psi is injective. And the type of this singularity is very much different from the type of this singularity on the left. And that's basically very important for the optimization process, because if I introduce one function, one loss function over this hospital curve, that point every time becomes critical point. So we call it attractor, basically. So I hope that these two settings are clear, because that's the main point of this talk, basically. So now let's move on a bit. I just want to give you one overview that what we can do for every neural network architecture. We assign a set, which is a set, we call it this neuromanifold that we discussed 10 minutes ago, basically. We assign a set. This set is containing all functions in your neural network, basically. So we want to understand the geometry of this set. And we provided this dictionary. So on the left, we have machine learning. On the right, we have algebraic geometry. So I talked to you about this dimension, volume, singularities, fiber of the parameterization. And I didn't discuss about this dynamical invariance, so it's not the main point of the talk today. But on the left, we have these concepts in machine learning, like sample complexity, how many samples you need so that your network generalizes well. Expressivity, which means basically how much your network can learn. Implicit bias, it means that, so basically your network has tendency towards specific functions. And this topic about geometric deep learning, so that you want to understand this invariant theory. And dynamics of learning. So what we have is that there is this big connection between sample complexity and volume and dimension of this set, this neuromanifold. Expressivity is also connected to dimension and volume. So the third part that I'm going to discuss a lot today is implicit bias, that is related to the singular points of the neuromanifold, fiber of the parameterization, and invariant theory and dynamics of learning and dynamical invariance. So basically, what I'm going to tell you today is very much related to this picture. We have every point in this neuromanifold that are smooth is fine, but these points that you see, they are singular points, and they are going to correspond to basically to functions in your network that a neuron or two neurons or several neurons are off. So that's going to be the main point of the talk today, actually. And there is a sequence of papers, like starting from understanding linear settings, the neuromanifold of linear convolutional networks, and then to polynomial setting, polynomial convolutional network. And then it was in January that we wrote this position paper that is called An Invitation to Neuroalgebraic Geometry. So basically what we can study. So there is a sequence of papers that you can look and what we can do with algebraic geometry. So now let's move on to the architecture that we want to analyze. So we focus on feed-forward neural network. And as you know, feed-forward neural network is basically composition of a specific function. So you have this affine maps based on the input data. And you have the activation function. And you see the composition of these functions like f. So that's the structure of your network. Okay. So we are going to focus on feed-forward neural network, mainly on MLPs and CNNs. And it comes to the definition of neuromanifold. So what we call neuromanifold, I briefly mentioned intuitively what is a neuromanifold. But a neuromanifold is a set representing all functions in your neural network, basically. So all the functions that are available in your network, it gives you a set, basically. So in mathematical terms, so this curly M, it contains all the functions that your network parameterizes. So every tuple of matrices, biases, gives you one function, and every function is a point on your neuromanifold, basically. And that's kind of an imaginary object that your neuromanifold probably looks like this. So now it comes to the train. We have a question?
I was just this is relevant to what we were talking about before. Yeah. But you can keep going. It's not a question.
Yeah. So at the end of the day, we have this optimization task in machine learning, in the deep neural network, for instance. So we have a loss function from the space of parameters to R. So we want to find basically based on the given data, input and output data, we want to find which parameter in the domain gives us the local minimum of this loss, or fortunately global minimum. So I'm going to write this loss function as composition of two functions. So as I said, this neuromanifold, so we have this parameterization map. So I send these parameters to the corresponding function with this parameterization map phi. So basically, this tuple of matrices and biases goes to this corresponding function. And then I can see the loss function on the neuromanifold, right? It's just writing the same curly L, this loss function, in a little bit different format. So it's a composition of two maps. So it's another loss function, a small L, and this parameterization map phi. And as you can see, I can study this part. It gives us a lot of information. So I want to understand at the end of the day the geometry of this M, because the geometry of M gives us a lot of information about this whole optimization process. So that's basically the observation. Understanding the geometry of the neuromanifold gives us a lot of information about the optimization process. So at the end of the day, it's going to look like something like this. We have this true function. I mean, this is the ground truth function, f star. And this big purple curve is our neuromanifold. And imagine that this optimization task is just finding the closest point on the neuromanifold, basically. On the right, you see this graph, for instance. So when f is here, I get this distance, and f moves towards right, then I find this local minimum. So f is here, I get the closest distance. So that's why I get this local minimum. And in here, I have these singular points, and you can see also its effect on the loss function. And one thing that is very interesting, if I have another ground truth function like g star in here, and I look at this again, this closest point problem, I still get that I still can find the position of these singular points on the neuromanifold. So that singularity on the neuromanifold is again a critical point for the loss function. You can see it in here. So that's why singularities on the neuromanifolds are very important. You can see its effect on the loss function. But there is a big caveat to this. It's not as easy. I mean, that picture is nice, but it's not the true pictures that happens in optimization of the neural network, because neuromanifold originally sits in an infinite dimensional ambient space. So M is sitting in the space of all continuous function, basically. So the optimization is not as easy as I showed you. So what we do with algebraic geometry, we want this ambient space to be finite dimensional. So we want to have some control. So what we do, we use polynomials as activation function. For instance, we can approximate any activation function with polynomials like this. I can approximate ReLU, for instance, with degree 2 polynomials, degree 4. It's again a consequence of Weierstrass theorem. So the hope is that I'm not going to use in a training task all the parts of all the real numbers in the domain of my activation function. So the hope is that if, for instance, I approximate one activation function in a very large domain, like this ReLU that I showed you, then the performance of my network would be the same as the original one. But the good thing is that the ambient space is going to become like finite dimensional, and it's easy to analyze the optimization process. Just seeing one example, this shallow network. So we have this 2 by 2 matrix as the first layer, and the second layer is just 1 by 2. And let's the activation function be x squared. If I see the output of this network, and I compute the output of this network, it's going to be looking like this. So the output of this network is like looking at these coefficients of degree 2 polynomials based on the input variables. So the ambient space already become finite dimensional. That now is actually 3-dimensional. So that's the main intuition. The ambient space of the neuromanifold becomes finite dimensional. So what else we know when we consider polynomial activation function? So this theorem is the consequence of Tarski-Seidenberg theorem. It says that the neuromanifold of any neural network with polynomial activation function is semi-algebraic set. It means that M can be described by a finite set of polynomial equalities and polynomial inequalities. So that's going to be the shape, for instance. So in the surface, this Whitney umbrella is the, for instance, the zeros of this polynomial. And I can have like polynomial inequalities. So it's the same f1 equals 0 and f2 bigger or equal than 0. So you see that your space can be cut, so you get some boundary points. But the whole point is that this neuromanifold is the zeros of some polynomial equations, and it satisfies some polynomial inequalities.
Sorry, is there an easy way to understand where do the inequalities come from?
So it relates to the cylindrical decomposition, I mean, the way that we construct it. But I can tell you in one example, for instance, if you send x to x to the power of 2, so you have a map from R to R, right? So you don't see all the points in the real numbers, but you see this the half line. So the image of this parametrization, it gives you like all t bigger or equal than 0. So in one example, maybe it's clear, but at the end of the day, when you want to construct this condition that gives you the image of this map, you want to basically eliminate the variables. And based on that, you get the inequalities. So it's not super easy, but in some examples, I hope that it is clear like this.
Okay, thanks.
Yeah. So now it comes to like experiment, for instance, one small experiment that if I replace some activation function with its polynomial approximation, is it true that we get some good result? It turns out that if you're careful about designing this polynomial activation function, the answer is yes. For instance, on MNIST, what I did, it was like I constructed like 3-layer ReLU network, and I got like accuracy of 98, 99%. And I replaced this ReLU with this polynomial activation, polynomial approximation. And we got quite a good result, basically. So it means that if you're careful about the choice of this polynomial activation function, so not everything's going to blow up in the optimization process, then you can get a decent result and probably something like the original activation function that you had in mind. And yeah. And as a summary, what we have again, we have this loss function, we have this neuromanifold in the middle between. We want to understand the geometry of the neuromanifold, because the optimization process actually is related very much to the geometry of this neuromanifold. So before going to, further results, if you have any question, please ask. It was just the basic things about algebraic geometry and machine learning.
Hi.
Hi.
I was kind of curious. You said that the motivation for replacing activations with polynomials was to make the neuromanifolds finite dimensional?
No, it's the ambient space neuromanifold.
The ambient space?
Yes, the dimension of neuromanifold doesn't change because it's like.
Yeah, that was kind of my question. Like, I didn't see how neuromanifold became finite dimensional when it was not before.
Yeah, exactly. So the neuromanifold is always finite dimensional because you have finitely many parameters in the domain.
Yeah. Mm-hmm.
So
what's becoming finite dimensional is the ambient space, which is
exactly. So the ambient space becomes finite dimensional, and in many senses, it becomes easier to see this loss function, or at least this optimization in here, when the ambient space is like, I don't know, is in R1000.
Oh, okay. You're just saying, okay, but even still, like even without making that simplification, you can still say that you have, I don't know, some projection of the ambient space that M is sitting in that is, that's injective over M, because, if you have finitely many parameters, you can determine the network by like its value and finitely many inputs. But for you, it's important that like you have a nice space.
Yes.
Nice,
yeah.
Okay.
Well, one of these projections is actually is the same as taking polynomial activation function is true. So if you have like analytic activation function, you project it to the space of, I don't know, degree at most 1,000 polynomials based on the input variable. It's like taking like degree 10 polynomial as activation function. It's the same kind of. Exactly.
Okay.
But also, this is one motivation. The other one is that we have tools in algebraic geometry to understand the geometry of this neuromanifolds, because M, as I said in this theorem, it becomes semi-algebraic. But it's not true if I pick, I don't know, arctangent as activation function. It's not going to be semi-algebraic. It's going to be a little bit.
Yeah, it's going to be something weirder, and you need to simplify somehow. Got it.
Yeah, exactly. So now it comes to some of the results that we have. As I mentioned, this parametrization is very important. So the fiber of the parametrization is important because one way to get singularities was having unusual fiber. So let's see what happens for the MLP. So it's fully connected network. So the theorem says the following. Consider an MLP with L layers. So what you do is that you send this weights, this tuple of matrices to the corresponding function in here. I just, for simplicity, didn't write the bias. So this theorem says the following. For generic choice of WL, so for almost any choice of this weight matrices, and sigma to be polynomial, we have the following. For almost all choices of activation function, the fiber of this parametrization consists only finitely many tuple of weight matrices. and they describe by the following. So we get these WIs, but also permutation matrices. So that set is like finitely many. So that set is finite, the cardinality of this set. So if you include all the permutation symmetry, all of them gives you the same function as this fx. I call this fx. So you have this, in the first layer, you have P1 W1. In the second layer, you have P2 W2 P1 transpose. So this P1 transpose and P1 is going to cancel out. So we can actually identify the fiber of an MLP with polynomial activation. So it's with ReLU, it's going to give you more fiber, because in ReLU we have also a scaling, positive scaling symmetry. But for arbitrary choice of a polynomial as activation function, we only get these symmetries in the fiber. And one of the consequences of this is that since the fiber of a generic function, the fiber of the generic point of the parametrization map is finite, the dimension of the neuromanifold, which was one important quantity, is the same as the total number of the parameters that you have in your network. And a little bit more to this, I said that for generic choices of tuple of matrices, but now I'm going to tell you what is not generic. So in MLP setting, the following thing is not generic. So imagine that you kill a neuron. So basically when you kill a neuron, so you make your architectures a little bit smaller. So we call this subnetwork. And my claim is that non-generic fibers come from subnetworks. So how you get subnetworks is the following. Either you put 0 column, or you have repeated rows in your matrix. And when you construct this WL sigma, WL minus 1 sigma 2 sigma W1 X, this function corresponds to a function that you can construct it with a network that is smaller, because I killed a neuron by doing this procedure. And if I look at the fiber of this function, so basically the preimage of the parametrization, when I look at F, is not going to be only this permutation things that we saw in the previous slide. So in the previous slide, we saw that only finitely many points exist in the fiber. But if I consider this F, I'm going to have like the dimension of this guy. So the dimension of this guy is going to be strictly larger than 0. So we are not going to get only finitely many tuple of matrices. So it means that my parametrization maps a lot of tuple of parameters to only one function. So there is some sort of a collapsing effect will appear. And what happens in the neuromanifold, you will get this singularity just because of a lot of things will collapse to one point. So imagine that the plane, so that's maybe the better way of showing it. Like, let me see if, yeah. So imagine that you have the following. This is your domain now. Each line are mapping to this line in here, but the whole line in here are going to map to one point. So you collapse the positive dimensional thing to one point, and you will get a singularity, just like in here in this Kohn. So in the MLP, actually, the subnetworks are going to give you, the tuple of weights that correspond to subnetworks are going to give you singularity in your neuromanifold. And a little bit more to MLPs. So that's the kind of main results that we have. Again, consider one MLP, and consider quadratic loss on this when you consider the optimization. So we have the following setting. Phi is the parameterization, and this small l is just a loss function that is induced by this big L. Now consider this theta 0, the space of all parameters, the set of all parameters that correspond to the subnetwork. Then we have these two following things. All functions in phi of theta 0 are singular points of the neuromanifold, because a lot of things are going to map to one point. So we get the singularities like this. And the other thing is about being critically exposed. So I just briefly tell you what I mean by being critically exposed. For every choice of input and output data, there exists a tuple of these weight matrices theta 0, a small theta 0 in the subnetwork, such that theta 0 is the critical points of the loss function. So subnetworks are attractors of the loss function. And I will explain in one example what I mean by the second part. The parameterization of the cuspidal curve is a perfect example. Again, consider your parameterization to be just a simple from R to R squared. So you send t to t squared and t cubed. And if you remember, that parameterization sends the line, this affine line or this real numbers, to the following picture. And in here is like the singularity. And consider the following optimization problem. So you pick one point, so that's going to represent your true function, like f star. So it's a point in R2. Now consider the square distance function, so that's your loss function. So you want to compute the distance, the square distance between the points on your set from u and v, this pair u and v. So I write this distance function as the following, right? So for computing the critical points, I need to take the differentiation with respect to t. And when I do that, L prime looks like the following, right? It's just a simple computation. But now look at this now. For every choice of f star, the point t equals 0 is a critical point for L, because L prime of 0 is 0. So the Jacobian vanishes. So it doesn't matter where I picked my data point or my data manifold, this f star. T equals 0, that singularity is always going to be critical points of my loss function. So the way that you can visualize the previous result is that t equals 0 corresponds to this point, this cuspidal point in my curve. And this is here like f star. When I see the distance from f star to this curve, that red point is always the critical points of the loss function. It doesn't tell you that it's going to be local minimum necessarily, but it's going to be critical points of the loss function. Right?
One thing there is, it seems like actually before you even get to that point of considering the sort of critical points of the neuromanifold, sort of the critical points of the loss function in that R2, that the parameterization you've chosen means that, because you're going from t to t squared, t cubed, just the parameterization implies that you're going to get your first derivative of t is going to be 0.
Right.
T equals 0.
Right. You're asking that if it's somehow it's a matter of choosing a parameterization, that phenomena, or
yeah, it's I was going to say that you gave a justification in terms of the image of this parameterization map, but it seems like like the critical point condition is a differential condition on the parameterization map at t equals 0. So it sort of depends also on the sensitivity of.
That's true. That's true. I mean, not for this case. So whatever parameterization you pick, this phenomena happen. But in general, what you're saying is true. Not for this example, though. But remember that for this neural network, the parameterization is given. So with that assumption, I'm saying that it is critical. Subnetworks are critically exposed. So in neural network, we have a fixed parameterization. So what you're saying is valid.
To be clear, I said that not to mean that you were bad for looking at the parameterization, but that in some sense the justification that I would immediately come to would move towards the parameterization.
Right. Yeah. I agree. I agree with the comment. Yeah.
I'm also curious about this example because we're saying that we're thinking about geometry of the neuromanifold, but it's also possible, I suppose, for a neural network that maybe there's a point where the neuromanifold does not have a singularity, but because of the way it's parameterized, a certain point is more critical than you would expect in the sense that maybe the Jacobian of the parameterization vanishes.
That's completely true. So the results that we have, we don't say that what are the we don't say we specify the fixed set of parameters that correspond to subnetworks, and those are critically exposed, like this cuspidal singularity. So I'm not. It might happen that there is a point on the neuromanifold which is smooth, but based on the parameterization, I get something that is critical for the parameterization. So I'm not claiming that also, right? So the thing that I'm claiming, fix this theta 0 to be this tuple of matrices that correspond to subnetworks, and based on the parameterization that we know, is going to be the critical points of the loss function. But at the same time, we analyze separately the first part, these subnetworks correspond to singular points at the same time. So it is true that it might be like critically exposed, but might not be singular points of the neuromanifold. So it might be like a third option to analyze that phenomena that you are mentioning. And we don't know because we don't really understand the parameterization of an MLP fully.
Okay, but I can kind of think of this as two properties. The criticality of a point on the neuromanifold implies that the Jacobian will vanish or do something funky. Not vanish entirely, but do something funky. But like the geometry of the neuromanifold it's a kind of a stronger statement. It's saying that no parameterization could possibly.
Yes. And to be honest, that's probably the case because, as I mentioned, for this cuspidal curve, so if your parameters are coming from the subnetworks, the geometry is so degenerate in some sense. It doesn't matter what parameterization literally you take for the neuromanifold, you still see the same phenomena. So it doesn't matter what. Yeah, exactly. But basically,
sorry, go ahead.
No, I just want to say that basically what you're saying is like that. It's really important that you're not fully connected the geometry of neuromanifold and the parameterization. You can have bad parameterization.
Yeah. Got it. Thank you.
Yeah, thank you so much for the questions. Now I'm going to switch the gear to convolutional setting. So in the convolutional setting, I just consider this simple architecture. So you have this tuple of filters in Rki. So every Wi is a vector in Rki. So the size of this Wi is actually Ki. And I consider the following architecture. So it's based on the convolution. So these SIs are just the stride. We call this stride, doesn't matter right now. So it's just a feed-forward neural network, but instead of having fully connected, we are in the convolutional setting. And still, I can look at the neuromanifold, so the image of this parameterization. And I also consider polynomial as activation function. I want to see what's the difference between this setting, this CNN, and the MLP. So we have the following result. For generic choice of polynomial activation function, high enough degree, we have the following result. The parameterization is regular, basically at every tuple of filters that are not zero. So in the MLP, the subnetworks were actually critical points of the parametrization also. But in CNN, they are not going to be critical points of the parametrization. So if I want to explain a bit, that MLP part give us this parametrization of cuspidal curve. But if you remember, I also parameterized the nodal curve, which was looking like this. And it was an immersion, so it didn't have any critical points for the parameterization. So R maps to with phi to this nodal curve. So there is no critical points for the parameterization. And one thing more, which is very similar to this nodal parameterization of nodal curve, the parametrization of a CNN, this CNN, is generically one-to-one. So every tuple of filters maps to one function, generically. And also the remaining fibers are finite. So there is no like positive dimensional set maps to one function like MLP. So it's completely different setting. And again, based on this property of generically one-to-one or having a finite map, we can compute the dimension of the neuromanifold is again the same number of parameters that you have in your network. And the last part that is very important, we can still consider the subnetworks. The tuple of parameters that correspond, the set of tuple of parameters correspond to subnetwork is not going to be critically exposed, but they are going to give you singular points. So it's again similar to parametrization of a nodal curve. So the preimage of every point is just at most one point. At most finitely many points. And you still get this singularity. And that singularity is not going to be critically exposed. So it's not going to be attracted by this optimization task. And if I'm going to show you how it looks like, on the left, you have something like the neuromanifold of CNN. On the right, you have a neuromanifold of MLP. You have that, on MLP, you have that edge. So that's the subnetworks and this gold line in here. And this gold line is going to be attractive to the optimization process because if F star is here, there is this point that, like this F, that's going to be critical points of the loss function that I have. But in CNN setting, because of this multi-crossing singularity that we have, these singular points, these subnetworks are not going to be attracted by the optimization process. So there is a big difference between CNN and MLP in terms of their neuromanifold. So it is true that in CNN, is not going, the subnetworks are not going to be attractive, but there is a catch to it. I try to picture this the way that I think. So look at the left on CNN. That point, these points, like in the middle, they are the singular points of the CNN. So it is true that blue points are not going to be attractive, the subnetworks, but a lot of things are going to pass from this blue region, this blue singularity. So the singularity corresponds to the subnetwork. And the density of the functions in here, if you look at it, they are more. So what I'm saying is that when you optimize a CNN, even though that the subnetworks are not going to be attractive, but a region, a neighborhood around the subnetworks are going to be attractive because the density of the functions are more than the density of the function over the smooth points of the neuromanifold. So it's more dense around singularities. But in MLPs, just because you get these cuspidal singularities, if a true function is here, there is a good chance that you converge to the subnetwork, to exactly the subnetwork. But it's not the case for CNN. So what I'm saying is that initialization, correct initialization, or random initialization is MLP is way more important than CNN. So whatever you like, you can initialize your CNN and it converge to something good. But it's not the case for MLP. So if you initialize in the subnetwork, you will remain in the subnetwork. So you might get a very bad accuracy, for instance, because of this cuspidal phenomena that can happen. So yeah, that was basically the summary of this paper. And if you have any questions, you're welcome to ask.